In today's video, we're going to be looking at the section 1.1 guide, and we're going to be going through the examples. So example 1, we're looking at a die and trying to understand if it's fair. So if a die is fair, then that would mean that it rolls the number 5 1/6 of the time in the long run. So in order to understand this, I'm going to collect a sample of these rolls forever and ever and ever, but I'm only going to do it 60 times. I roll the die 60 times. I find out that I get 14 out of 60 fives from my smaller sample, and that gives me the statistic of 14 out of 60, or 23.3%. So that's my statistic. All right, let's go through these. So A says, describe the variable. Is it categorical or quantitative? So the variable here is, if I roll a die, what am I getting out of that? Well, I'm looking at it and I'm getting out the side that it landed on. So I'm going to call that just side to shorten it up. So it's the side you land on. And that's categorical because it has options: 1, 2, 3, 4, 5, or 6. Every die roll, I look at it, I put it into one of these boxes. The 1 box, the 2 box, the 3 box, and so on. What's the population? The population here is all the possible rolls of my die that I'm interested in. Because remember, to be 100% sure if it's fair, I would have to roll it forever. I can't do that, and so I take a sample in part C. I grab hold of 60 rolls, and I can actually do that and look at that. So those are the rolls that I did. So it's this little subset of the population. D, the parameter of interest is the long-run proportion of die rolls that land on 5. So again, try to notice the connection here. The parameter is going to be go to the population and measure something about it. So if the population is all the rolls I could ever do, then how can I measure something about it? I could look at the proportion of times it lands on 5. So again, the population's all the rolls. The parameter is, how do I measure something about that to help me answer my question? It's a proportion, so we're going to call that pi, and it's unknown because I can't roll the die forever. All right, E, identify the statistic. Well, again, the connection. The statistic looks a lot like the parameter, it's just the statistic is connected to the sample. So S and S are connected, where here P for parameter and P for population are connected. So the P's go together and the S's go together. So the statistic is, it's the same thing as the parameter, except for instead of being about all the possible rolls, it's only about the 60 I did. So it's 14 fives out of 60 total rolls. And we know that because we actually can calculate it. Okay, so definitely make sure you read this. But what we're going to be doing is we're going to be asking the question, or at least trying to answer the question, is this statistic here that we got, is that usual or unusual if my die is fair? So this is very important. If my die is fair, then does my statistic here that came from 60 rolls, does that fit the idea of a fair die? Well, so how do we do that? How do we know what 60 rolls is supposed to look like from a fair die? So in other scenarios, as we talked about above, you make an assumption and you immediately can build a model from that. But it's not so easy all the time with things like rolling dice, so what we're going to do is have a computer build this model for us, and then we're just going to use that. So here's an example of that down here. There's another video of me demoing the website for this, so make sure you go check that out. But this is what was plugged into each of the boxes. The probability of heads here is what should happen if it's a fair die. This corresponds to 1 out of 6. The number of tosses, well, that's just what was your sample, 60 rolls. And then the number of repetitions is up to you. We'll usually do 100 or 1,000. The more you do, the better. So either of those is fine. Hit draw samples, and we get a picture like this. So what is this picture? This picture is showing you what it looks like if the computer rolled a fair die 60 times, and then each time it did that, it took the proportion of fives and made a dot. So each dot here corresponds to the computer rolling a fair die 60 times and then telling you what happened in terms of how many 5s it got, specifically the proportion. So what is this doing? This is showing you that, okay, if I have a fair die and I do your experiment that you did with the 60 rolls, then these are the possible outcomes I could get. And what you notice from that is there's a whole bunch of these experiments, you can call them, just so we have a word on it, or simulations. There's a whole bunch of these that got pretty close to what we put up here, which should make sense. It's a fair die. So if I roll it a bunch of times, I should probably get about 1/6 of the time it hits a 5. That's right in the middle here. You could see the mean is right at that number. So this middle is about 1/6. But this is a random process. So there's randomness, and one way you could think about this if you want to is you could think about it in terms of luck. So every time the computer does the 60 rolls, sometimes if 5 is good, it got lucky over here and it got more 5s, or sometimes it got unlucky and it got less 5s. But we're not specifically interested in each case. What we're interested in is what's the overall pattern. And the overall pattern is you're going to be pretty close most of the time, because most of the dots are close. You're going to be pretty close in here. And sometimes, it's much less likely or common, but sometimes you'll get lucky or unlucky. But most of the time you're going to be pretty close. Okay, so that's what this picture is. We're going to do this over and over and over again, but that's what we have to try to get from it. All right, so you can kind of look through here. F says, what's the chance model? We've kind of described that. The chance model is showing 100 simulations. Each dot is a simulation of 60 rolls of the fair die. Okay, what's each dot? Each dot represents the proportion of 5s rolled out of 60 rolls. So each dot, in this case, it would be 3 out of 60 rolls were 5 for that one simulation. Okay, H. Each person who recreates the simulation on the computer will get a slightly different chance model. Go try this. So whenever we're doing these things, make sure you're actively trying to do and answer the questions before I get there, trying to use the simulation too, so we can kind of try to stay together. So do this. You should get a picture that's very similar to this, but not the same. So why then will everyone have a mean that's close to this? So mean, remember, just means middle. And that's because we told the computer that's what should happen. It's a fair die. So then, like we said already, everyone who does this, sometimes the computer will get lucky, sometimes it'll get unlucky. But for everyone, most of the time the computer should have statistics, as in the proportions that they get, right around the middle. All right. If the die is fair, what types of sample statistics would be normal, usual, expected? And when we're saying sample statistics, remember, we're just talking about the dots here. Which dots are usual, expected, fit the pattern? And we're going to put math behind this a little bit later, so don't worry if you would answer this a little bit different than me, as long as we're in the same ballpark. So in this case, I said between 6 to 15 5s fits the picture. So I'm thinking that this pattern kind of looks like 6 to about 15 fit in there. And maybe you can make an argument for 14. But that's where the main chunk of these statistics are. Okay, so on the other hand, it would be unusual then to be away from this pattern. So then unusual would be less than 6 over here, because that just doesn't happen very frequently according to our chance model, or bigger than 15 over here. Anything bigger than 15 doesn't seem to happen very often. It can happen. You can get super lucky every once in a while, but it's not usual. All right. So what's our conclusion? Well, our statistic, our actual stat, when we did it, was 14 out of 60. So I go up, I say 14's here. Well, it's a little lucky, but it still fits the picture pretty well. It fits the pattern, so I'm good. If our statistic fits the chance model pattern, then we say, okay, the chance model is plausible. No complaints here. I believe you have a fair die. I'm not 100% sure, but it fits. Okay, example 2. So in example 2, we've got 3 candy bars on the market in competition, Yummies, Crunchies, and Tasties. So last week there were 10,000 candy bars sold in total, and Yummies had gotten 40% of those purchases. So what we're wondering is okay, Yummies got more than a third of the purchases. Is that because people really might have a preference for Yummies, or is it just chance that Yummies had a good week last week, when really it's pretty spread evenly between the 3 companies? That's our big question here. Okay, so the first thing we have to do is think about, well, what would it look like if the 3 companies really were just even across the board? Well, if that was true, then every week the purchases should look like a third, or 33% Yummies, 33% Crunchies, 33% Tasties. That's what it should look like if it's really even across the 3 companies. Okay, so let's dig into the actual terminology here. So for A, describe the population. In order to really know if one of these 3 companies was better or worse or whatever we were looking for, if it wasn't even across the 3, we would have to look at all of the candy bar purchases sold by the 3 companies forever and ever. So we can't do that because we can't go into the future, can't go into the past, too far at least. So we can't do that. So what we do is we look at a sample of the 10,000 purchases from last week. That's what we can actually get our hands on. Okay, so I'm looking at all these candy bar purchases. What's the parameter? What's the way I measure something about those in order to answer my question? Well, the parameter in this case is the proportion of purchases of those candy bars, all candy bar purchases, that were for the Yummies company. If I really knew the proportion of candy bar purchases that the Yummies company got, I would be able to answer my question. Unfortunately, I can't do that, so I don't know that. It's unknown. But, just like we've seen before, I may not be able to answer that for all purchases forever and ever, but I can at least take a sample of them and see what happens in that sample. That's my statistic. Remember, S with S, P with P. So my statistic is, I'm looking at the proportion of the 10,000 purchases that happened last week that were the Yummies. And I ended up getting 40% of them. That was just given to me. And we know it because it's the statistic. What's the variable? Well, what am I looking at? I'm looking at a purchase. I'm looking at all the purchases. Each purchase, I look at it and I get info. What's the info I get from it? The information I get is the variable, or the candy bar company, or company for short in this case. It has possible options, Yummies, Crunchies, Tasties. Is this categorical or quantitative? This one's categorical. Again, look, I've got 3 boxes. Every purchase fits into the Yummies box, the Crunchies box, or the Tasties box. Okay, so again, we're at the point, I've got a statistic. I know what it should look like if the 3 companies are all equal. How do I compare those two to know if my statistic fits? I've got to make a chance model. So I go to the Rossmann chance applet. I put in this number here, which remember, this number represents what if they were all the same. That's 1/3 as we had discussed, so I put that in here. Okay, the next one is, well, all right, you actually looked at some data. How many data points did you look at? We had 10,000 purchases. That goes here. Number of samples, that's 1,000. That's just because I chose that. 100,000, whatever you want to do. And this is the distribution. So what is this saying? Again, just to kind of reiterate this is saying if the 3 companies are about equal across the board in terms of preference for people buying their candy bar, then when I look at 10,000 purchases and I say, okay, well, what proportion did Yummies get? This is what I should get. When I look at 10,000 purchases, look what happens again. It looks like most of them are around 1/3 of the purchases were Yummies. We expect this. We're telling the computer this is what should happen. But sometimes Yummies had a good week, right over here, 35%, pretty good week for Yummies. And sometimes Yummies had a bad week, 32%, or This should probably be 31%. So this chance model is showing you that there's a pattern to this randomness, which is, I know, kind of interesting, right? Sometimes we have this random idea, but there's patterns to it. And the pattern is we're mostly getting things pretty close to even between the three groups, but sometimes Yummies is lucky, sometimes it's not. Okay, so with this chance model in our head, how does our actual data compare? So our data was 40%, or 0.40. So go find it on the picture. And I can't find it because 0.4, if I follow this, would be all the way out here somewhere. So 0.4 is so far out, the computer, in its 1,000 times it did this, never got anywhere close to it. So 0.4 is way away from this chance model that we have here. So immediately in my head, that's making me think, something's wrong with this chance model because my data is nowhere near this information, this data. So just to kind of reiterate each of these pieces, what does each dot represent? Each dot represents 10,000 sales that we simulated. So you could think like the 1 week. Each one of these dots is a week of 10,000 sales we're looking at. And each dot, the actual number, is the proportion of sales Yummies got. Again, each person who does a simulation will get something different, but we know that this chance model for every person who does it should be centered around this number, because that's what we're telling the computer to assume when they do this work. If they really are just being purchased randomly, 1/3 of the time each, then what types of sample statistics, or dots here, for the purchase of Yummies would be normal, usual, or expected? So again, we just look at the picture and say, okay, well, where's the thick of this picture? And there's some debate here, but it seems kind of like once we get over to the maybe 0.32 and somewhere around 0.34, it seems like this kind of is the middle, and then we've got some stuff out here it happens, but it's very infrequent. All right, so I said between 32% and 34% would be normal. If there was another week and Yummies got anywhere near this proportion, 32 to 34%, I'd say, okay, that's fine. They could still have an equal share at 33%. And again, remember, they got a little lucky. They didn't get lucky. That's fine. That's okay for us. Any values outside of those, see how this pattern keeps happening. There's some range inside, and then outside are these unusuals. So I would say anywhere over here or over here, to me, seems unusual. It really shouldn't happen if Yummies really has a 33% share of the market. Okay, so I've kind of already answered K, but we should just say it again. Our statistic, 40%, is well outside the normal range that we just said in J. So that means our statistic does not fit the model. And so we think because of that, our assumption that Yummies really has 33% of the market might be wrong. There you go. We've got evidence against our assumption. So we're saying, we might want to throw that out. Okay, let's go to example 3. So example 3 says, suppose someone tells me that the mean GPA for all currently enrolled DCC students is 2.74. I'm not sure I believe what this person told me, so I'm going to go collect a sample of these students and see what their GPA is. And then I'm going to try to compare those two things. The sample I had a GPA of 2.86. So let's go back through, taking these steps all over again. What's the population? Who am I looking at? I'm looking at DCC students. Okay, describe the sample. Well, out of that big group, who did I actually talk to, or who or what was I actually looking at? The 85 students. That's who I actually grabbed onto, not really, but grabbed onto and got information from. Describe the parameter. So the parameter, again, is what do I measure about the population? Remember, P, and P. What do I measure about the population, DCC students, to answer my question? Well, what do I measure? I measure their average GPA. That would just directly answer my question. It's not always that obvious, but a lot of the times it's exactly that. So if I get the average GPA for the whole group of students, I know my answer. Now, to me, this is unknown, but the school has records on this, so technically this is something that could be known, but let's just pretend we can't know that. And the symbol is mu. So this is not a typo. This is a Greek letter mu. Okay, let's identify the statistic. So the statistic, remember, S, goes with S, is similar to the parameter. It's just apply it only to the sample. The average GPA of the 85 students, which is 2.86, and that symbol is X bar. And we know it because it's a statistic. Let's describe the variable. The variable is GPA. What do I actually get from each student when I talk to them? I get their GPA. That's the variable. Okay? It's quantitative. So it's quantitative for two reasons. One, I look at a GPA, I get a number back. Okay? And even more importantly, if I have a group of people's GPA, it's very natural and it makes sense to average those numbers together. So they're numbers one that I can average. All right, so we're quantitative. So chance models are a little more difficult to explain how to create compared to, for quantitative compared to categorical. I think it's fairly natural to say, oh yeah, the computer can just flip a coin if it's 50%. Like, that makes sense. We'll talk a little bit more about how to make these chance models for quantitative data later. For now, I'm just going to show you what they look like. And there is an applet that can do this, but you have to put in a little more information than we're doing, and there's extra stuff we have to understand to create this. Okay, so here is our distribution. Again, we've seen pictures like this already, so hopefully this isn't too bad to see. We told the computer, I want you to go sample 85 simulated students, but assume that those students come from DCC students who have a mean GPA of 2.74. So remember, we're going to say, let's assume my friend is right. Let's simulate what it would look like to ask 85 students, and then ask another 85, and another 85, and another 85, and just keep doing that. And then we're going to look at this picture, which is the accumulation of all of those 85 students we looked at to see what their GPAs would be. Okay, so each one of these little squares in here would represent the average GPA of a group of 85 students that we pretended to go ask. All right, each student who does this will get a different picture, except that their picture should have a middle that's very similar to this number. Because remember, that's what we're telling the computer to assume. Okay, so this, even though it's quantitative and we were doing categorical before, this same idea of normal still works. You find around where the middle is, and then you ask yourself, where does it look like the chunk of this is? Where is the meat of this? And again, it's hard to tell, and it's definitely not as easy, I think, as the last two examples. But I said maybe 2.7 to 2.6, and maybe you might want to go to a little further out here. But it kind of seems like this is the middle, and outside those numbers, you're starting to get really unusual things that, again, could happen, remember, but don't seem to really fit the pattern. They're not very frequent. So I said 2.7 to 2.6 fits the picture. They're usual, normal. Anything lower than 2.7 or bigger than 2.76 will be unusual, because they just don't happen very frequently in this model. So what's our conclusion? Well, how do we make a conclusion? If this is what the samples of 85 students are supposed to kind of look like, assuming what our friend said was true, then we just take ours and compare it. Well, our sample was 2.86. That's over here. That's not even close to the picture. What that tells us is, we've got evidence against what our friend was saying, so maybe we think that they're not correct. That's it. So we think maybe they're not correct. We've got some evidence that they're not correct. Do we know 100%? Nope, but we have evidence that they're not correct. Okay, let's go to example 4. So example 4 is a soda company says that their cans contain an average of 12 ounces of soda in each can. If I go out and collect a random sample of 38 cans and my cans have an average of 11.92 ounces of soda, I'm wondering if the companies are actually underfilling their cans, or if maybe the 38 cans I grabbed, I just got a little unlucky and my average was a little bit low. But in general, they are true with what they're saying. So that's what our goal is. What's the population? The population would be all the soda cans from this company. So all the cans they're going to make, all the cans. I'd have to look at every single one, measure it, and figure out how much is in there in order to understand this. But that's so many cans of soda, I can't do that. So what I do is I take a sample of 38 cans. Okay, so the sample of 38 cans, I can actually look at those and test them. What's the parameter? The parameter is, what do I measure about the population? Remember, P and P. What do I measure about the population in order to try to answer my question? Well, if I had all the cans of soda, what would I do? I would find the average amount in each can. Mu. There you go. And that's unknown because it's not realistic to try to get every can of soda. What's the statistic? Remember, S with S. The statistic is going to be very much like the parameter, but it's applied only to the sample. So then the statistic in this case would be the average amount of soda in the 38 cans we collected. Not all of them, just the 38 we looked at. And we got X bar is 11.92 ounces. We know that because we actually have the 38 cans that we can look at. Okay, what's the variable in this case? Well, when I actually look at a can, what information am I getting? I'm getting the amount of soda in the can. So you might want to shorten that as amount of soda, or just amount. That's fine. But the variable in this case is how much soda is in the can. That's quantitative. It's going to be a number of ounces. And more importantly, it's a number of ounces that if we had 2, 3, 4 cans, whatever, we could average that together and it would make sense to say the average amount of soda in 3 cans, 4 cans. Okay, so again, here is another set of simulations here, another chance model, assuming that there really are 12 ounces on average in each can. We told the computer, okay, make that assumption, sample 38 cans, tell me what the average is, put it on the little picture here, like this little blue dot or blue rectangle, and then do that 1,000 times because I want to know what it looks like to do that many, many times. And then I have to take what I got and try to compare it. Okay, so that's our picture. We see that the middle is around 12, which we expect because that's what we told the computer is the truth about our cans. What does each little rectangle here represent? It represents the average amount of soda per can in 38 sodas. So each one of these is the computer going 38 sodas. Measure how much is in there, average it. All right, so as we've talked about before, why would everyone's simulation here be centered around 12? Well, that's what we told the computer is true. We told the computer the sodas really do have average of 12 ounces per can. Okay, if it's true that the average ounces per can is 12 for all the sodas, then what are the typical normal dots or rectangles in this case supposed to look like? So again, I'm going to say sample statistics, and once we get comfortable with these words, that's what we're going to want to say, right? But when we're actually, doing this now at the beginning, you can replace this with just the rectangle or dot, depending on what the picture you're looking at is. So which dots seem to fit the picture? Rectangles seem to fit the picture. And I said it looks like maybe 1197 to 1203, kind of this general grouping here. And outside of that, it happened out of 1,000 times, but not very often. It was unlikely to happen. So between 1197 and 1203 seem to be pretty normal. It happens. 1203 and 1197, when you get over there, you're getting a little lucky or unlucky for that to happen because it's not very frequent, but still within the range. So then anything outside of that, I'm going to call unusual. If I get a can with 11 or 38 cans with an average of 11.94 ounces, I'm going to say, that looks a little bit weird. Okay, so what's our conclusion? Well, 11.92 is actually quite far out of this range. It seems to be quite unusual because when the computer did this 1,000 times, it got 11.92 maybe once or twice. It's a little hard to see because it's not labeled, but there seems to be a very small rectangle here. So out of 1,000 times, it barely ever got this small of an average. So our statistic, our actual 38 cans, doesn't seem to fit this model. So then that means, I think this model that I had created, this assumption I made about really there being 12 ounces per can, seems like it might be wrong. And there you go. So I know this was a lot, and this is a long video, and I'll be giving little breakdowns so that you can jump around and know where to go in the video for certain examples. But hopefully you see that each of these examples, the structure is exactly the same. I set up a problem, we have a statistic, we have to, say what the parameter, the population, all that stuff is. But then the key piece is we say, okay, I'm going to make an assumption. I'm going to use the computer to do a bunch of experiments or take samples like I did under that assumption so that I know what's normal. And then I'm going to take my actual real live data and compare it to what's normal, what normal is, right? And then if your data fits in the normal, you say, okay, the assumption seems like it's probably fine. If it does not fit in normal, you say, it doesn't fit, so I think I need to re-examine my assumption. Now, you can't just say 100% that assumption's wrong and move on, but you've got evidence it's wrong. And then what we're going to do later in the class is try to talk about, how much evidence should I have in order to say, I really think I should throw out this assumption and look somewhere else, think about something else. So that'll come later. Right now, we're just trying to get a feel for determining when our statistic is usual, normal, in the pattern, or unusual, very far away, not in the pattern. All right, thanks for listening.